Okay, now I believe I'm recording.
Yeah, it's good now.
Okay, awesome. Sorry about that, everyone. So yeah, now we are officially recording. So let me erase some of this so we can see our next question, which is which terms now can be used to describe the pair of sugars that we see here? So now we have our original sugar, D-sorbitose. We have a new sugar, D-tagatose. And I'm just going to hide this so I can see it. Okay, so now we have two sugars. So take a couple minutes, compare these two sugars to each other, and decide what terms can be used to describe this pair of sugars.
I would say they're diastereomers. B.
Yeah, excellent. So they are diastereomers. So how do you know that? What is the definition of a diastereomer?
They have between well, more than one opposite configuration of each other. So like if they were all opposite configurations, they would be enantiomers. So
Mhm.
since more than one is opposite to diastereomer.
Yeah, great. So for diastereomers, we have at least one different configuration at chiral center, but not all. So if all the chiral centers are different, they're enantiomers, which we don't have here. So let's actually back up a little bit and take a look at our three different chiral carbons. So we already talked about how carbons number 3, 4, and 5 are the chiral ones. So at carbon number 3, they're different, right? Sorbitose has the OH on the right, tagatose has it on the left. Carbon number 4, they're the same. And at carbon number 5, they are also the same. They're both going to the right. So that means we do have diastereomers because we have at least one chiral center that's configured differently. They're not enantiomers because not all of the chiral centers are different from each other. What about epimers? What's the definition of an epimer? And is that what we see here?
Epimer differs on one chiral center, which this one has two, which I think would make it a not epimer.
So for this one, two of them are the same and one is different. So, which is the definition of an epimer. There is exactly one carbon that's different.
Yeah, that's what I meant.
Yeah. So they are also epimers in addition to being diastereomers. So how about this last one, anomers? So do we have, I guess, first of all, what are anomers? Do we have them here? Is it possible to have anomers here? Anybody remember about anomers?
Yes, I think it's possible to have anomers.
So when would we see anomers?
Um, like there's a change in the anomeric carbon, right?
Mhm. Yep. Yeah, so
So
when
you'd
do
have to
we,
have
go ahead.
a ketone or aldehyde in the open ring.
Yeah, so here we have our sugars in the linear form. So for our anomeric carbon, you only can have a configuration at that carbon when the sugar is closed into the ring form. So, so usually the anomeric carbon is the carbon that has the carbonyl group on it. So right now, that carbon is not chiral. yet. But when you form a hemiketal, in this case, because you have a ketone, then that carbon would have 4 different groups attached to it, and then it's possible for it to be, it is chiral. But right now it's not chiral yet. So we don't know which what configuration we'll have at the anomeric carbon yet, because these sugars aren't in the ring form. But it's so that's kind of yeah, just not possible here because we have only the linear sugars. And the other thing about anomers is that they would be the same at all of the other chiral carbons, except for at the anomeric carbon. So in this case, even if these sugars were in the ring form, they couldn't be anomers because they also differ at another chiral carbon, carbon number 3. Any questions about that for anyone?
I have a quick question, actually.
Sure.
So, would it be fair to say that all, maybe not. I was gonna say, could all epimers be diastereomers? But I guess like technically, if there's only one chiral center in a molecule, then it would be also an enantiomer, right?
So yeah, so all epimers are diastereomers, but not all diastereomers are epimers, because epimers have exactly one difference. Diastereomers have at least one difference. So if it had 2 out of 3 different, it would be a diastereomer, but not an epimer. It would need all 3 out of 3 different to be an enantiomer. Does that help?
Yep, thank you.
Okay, cool. All right, so let's move on to our next question, which is about linear monosaccharides. So, yeah, so first of all, I guess, how do you know this is a monosaccharide that we're looking at in this picture? Kind of a simplistic question. It's not like a trick. Just how do you know there's just, how do you know it's a monosaccharide? What does that mean?
There's only one sugar. It's not attached to a different sugar.
Exactly, yeah. It's just one sugar and it's by itself. It's not linked to any other sugars. And typically when we see our Fisher projections like this, especially when the sugars are drawn linearly, they're pretty much always monosaccharides. Once you start linking sugars to each other, they're almost always drawn in the ring form. So that's something to keep in mind when you're looking at pictures of sugars and the different forms they can be in. So, all right, so let's move on to the first question. So is this sugar in the D or the L configuration?
D configuration.
Yeah, excellent. How did you know that?
The bottommost chiral carbon has the OH group facing the right side.
Exactly. Yeah, so again, if we were going to go look at the sugar, we could number our carbons. So it has some number of carbons, 5, and then some of them are chiral. And if you look at the last chiral carbon, which here is carbon number 4, the carbon number 5 is not chiral. It has 2 H's bound to it. And then the hydroxyl group on that last chiral carbon is pointing to the right, which makes it a D sugar. So now that we know it's a D sugar, how can we categorize it based on the number of carbon atoms?
Like the fact that it's a pentose sugar.
Yeah, exactly right. So it's 5 carbons. So we use the prefix pen or pent, and then os for sugar. So it's a pentose, meaning a sugar with 5 carbons in it. And this is a separate idea than when it's in the ring form, when we can talk about how many members are in the ring. The number of carbons is not necessarily always the same as the number of members in the ring, but we'll get there when we start looking at the ring form. So let's now look at question number 3. Is this a ketose or an aldose?
And
Ketose.
Excellent. Yeah, I got a couple of ketoses. So yeah, we have a ketose. And anyone, how do you know it's a ketose?
That's a ketone group.
Yeah, exactly right. So this carbonyl group that we have that's on carbon number 2 is a ketone. And a ketone means that carbonyl carbon that I circled is bound to 2 other carbons. If it was an aldose, it would have an aldehyde, which would be on carbon number 1. And for aldehydes, as you recall, the carbonyl carbon is bound to 1 hydrogen and 1 carbon. Any questions about the differences between aldehydes and ketones? Cool. Okay. So now we can start looking at some, oh, right. And then this sugar, in case anyone was wondering, its name is D-xylulose. And so this is probably a good time to say, I don't expect anyone to memorize the structures of almost all of these sugars. I just expect you to be able to categorize them or identify information about them, sort of like we're doing here. There are probably a couple sugars that I'll want you to know the actual structure of, particularly glucose, maybe 1 or 2 others, and I'll let you know if there are other specific ones that you should know. So that being said, now let's start looking at some cyclic monosaccharides that are drawn in that ring form. So let's consider this sugar and first think about what modifications, if any, are present in this sugar. And anybody can shout it out.
Is it the presence of an amide group?
Yeah, so it has this modification on carbon number 2. So instead of a hydroxyl group there, you have an amide. So first we had an amination where we added the nitrogen, and then we did something else to that nitrogen. Do you remember the term for this part of the modification? Anyone?
Acetylation.
Yeah, excellent. So it's acetylation on that nitrogen, so we call it an acetylation.
I have a question.
Yeah.
When we are naming a sugar and we're gonna name it like N-acetylglucosamide, would the N-acetyl always be a carbon number 2?
Almost always, yeah. And in fact, if you ever see one written that doesn't specify which carbon it's on, you can always assume it's on carbon 2. I don't think I've ever run across any that aren't on carbon 2, but I'm sure they exist out there. But most of the ones we discuss in this class are, yeah, definitely on carbon 2.
Got it. Thank you.
Yep. And then just building on to this idea of acetylation. So in the lecture slides, we talked about how acetylation is a type of a more broad term for adding a certain type of group onto that amino. I know that's kind of a vague question, but does anyone remember the name for, like, let's say you wanted to add a longer carbon, hydrocarbon chain here. What would that be called? It sounds a little bit like acetylation, but it's more general.
Alkylation.
Close. So it's acylation. So alkyl would be if you just added hydrocarbons, but we're adding essentially a carboxyl group with hydrocarbons on it. So it's an acyl group. So an acyl group that only has 2 carbons is acetyl. If you have more than 2 carbons, or if you have any number of carbons, it's acylation more broadly. And we also talk about that in the context of fatty acids when we discuss those, which I believe is next chapter. Okay, so let's now look at this cyclic monosaccharide in general. So how would you categorize the sugar based on the number of carbon atoms?
Pentose.
So how many carbons are
Oh.
there?
No, there's 6.
Mhm.
I had those.
Yes, it is a hexose.
Oh, what just happened?
Yeah, so we have, I started numbering the carbons and then I stopped, but there's 1, 2, 3, 4, 5, and 6 carbons. So it is a hexose, even though not all the carbons are participating in the ring. It has 6 carbons, so it's a hexose. It also happens to be a 6-membered ring, but not all those carbons are in the ring. And so, yeah, so yeah, let's talk more about now number 3. Where is the anomeric carbon? Or which carbon number is it?
It's carbon number 1.
Yeah, exactly. So this carbon here is our anomeric carbon. It's the carbon that sort of used to have the carbonyl oxygen attached to it, which has now turned into a hydroxyl group. So this hydroxyl group used to be the carbonyl oxygen when the sugar was in the linear form. This oxygen that's part of the ring used to be an alcohol group that was on carbon number 5. Excuse me. But that then attacked the carbonyl carbon to form this this hemiacetal. Okay. So yeah, so does anybody, looking at this anomeric carbon, which, oh, and then I also want to mention that just for review, in general, the convention is when we're drawing these ring structures, we always have this oxygen here that used to be a hydroxyl group. The anomeric carbon is always drawn to the right of it. So 1 carbon over, that's going to be the anomeric carbon. And that's usually how it's drawn by convention, especially if you have a monosaccharide. Every once in a while, it will be flipped, especially if you have 2 sugars that are linked to each other by their anomeric carbons, because to have the anomeric carbons facing each other, you have to flip one of the pictures around because the 2 anomeric carbons had to be next to each other. They can't all be on the right side. So that's something to keep your eye on when you're considering pictures of sugars as we go through this. And can anybody tell me if this is the alpha or the beta configuration at the anomeric carbon?
It would be beta.
Yeah, it is beta, exactly. So the OH is pointing up. And so we have the beta. And this because we have a D sugar. So by convention, when your D sugars, when the anomeric hydroxyl group is pointing up, it's in the beta configuration. All right. I think I may have given away a future question, but that's okay. So does anyone have any questions so far about this?
I have a quick question.
Yeah.
Can you explain one more time what's the specific difference between acylation, alkylation versus acetylation?
Sure. So alkyl usually refers to just hydrocarbons, so adding methyl or ethyl or any other ol that is just carbons and hydrogens. When you're adding a essentially what used to be a I'm trying to think if it's always a carboxylic acid. It might not be, but if you're adding something that has a carbonyl group plus hydrocarbon, then it's acyl. So you can identify them because you have carbonyl and then you have some length of hydrocarbon chain next to it. So acyl, you sometimes will see them with an amide linkage like you see here. Sometimes you see them with an ester linkage. But the acylation refers to the carbonyl group that is directly attached to some other carbons that have hydrogens on them. And acetylation specifically refers to acylation with two carbons. So you have your carbonyl group and then two carbons, 1 and 2. And that's attached here on what was an amino group and the rest of our sugar. Does that make sense?
Yeah, that does. I think I just misheard you earlier, so I got confused. But yeah, that makes
Sorry about that. Yeah. Cool. Any other questions so far? All right. So yeah, so and then just to get used to looking at the names of sugars, this one is called N-acetyl-galactosamine. So our original sugar was galactose. We added this amino on position 2, which is not numbered here, because you can assume it's at carbon 2. And then we added an acetyl group onto that nitrogen. So in total, we have N-acetyl-galactosamine.
Isn't it kind of redundant with like N and then amine, like N, like why wouldn't it be N-acetyl-galactose?
So yeah, so if you said just N-acetyl-galactose, it would be incomplete because because galactose itself doesn't have an amino group on it. So acetyl refers to just adding the acetyl, which is this. It doesn't tell you necessarily that it's attached to a nitrogen. N does, but where is that nitrogen? You don't know, because if you just said galactose, I don't really need to write this, but if you just said galactose, you'd be referring to just this original sugar that had a hydroxyl group on carbon 2. So you have to specify first that you change that on carbon 2, you change the OH to an N, and then you added an acetyl onto that nitrogen. So you made 2 different modifications, even though we're just seeing that end result. Does that help?
Yeah, thank you.
Okay. Cool. So let's now keep thinking about the same sugar, N-acetyl-galactosamine. Now we have some more questions about how we can classify it. So let's start with number 4. Is it in the D or the L configuration?
Is it D?
It is D, yeah. And how do you know that?
Because the OH on the anomeric carbon is pointing up, which means it's beta, which usually means it's a D configuration.
Okay, so the position at the anomeric carbon is not related to whether it's D or L. So like you said, that here at the anomeric carbon, which is carbon number 1, the OH is pointing up and it's in the beta, but it could just as easily be pointing down and be alpha. But does anyone else have an idea for what tells us whether it's D or L?
Is it the group to the left of the oxygen in the ring?
Yeah,
The CH2OH pointing up.
exactly. Yeah. So our carbon number 6 that is coming off the end of the ring is pointing up. And that is what tells us that it's in the D configuration. So we'll almost always see them drawn this way because almost all the sugars we're going to think about are in the D configuration. And that's because it goes back to our Fisher projection. And when you think about the linear sugar, when you imagine turning it on its side and having the hydroxyl group from the 5 carbon attack the 1 carbon, the carbon number 6, like this was the original hydroxyl group that was part of carbon 5, right? So if you're pulling that carbon towards the right and you're in a D sugar, then carbon number 6 is going to end up facing up. It's a little hard to picture, but you can hopefully it kind of makes sense in your mind in some way. If it was an L, this carbon 6 would be pointing down. But like I said, most of the time we're going to see carbon 6 pointing up because we have D sugars. Any questions about that? All right. So do we have the alpha or the beta configuration? I know someone already said, but can shout it out again.
It's beta because the anomeric carbon and carbon 5 are pointing cis.
Yeah, exactly. So we're in the beta configuration. And so you can think about it as, since we're in a D sugar and the hydroxyl group on the carbon number 1, which is our anomeric carbon, is pointing up, it's beta. Another way you can remember that it doesn't matter if your sugar is D or L. So if the hydroxyl group on your anomeric carbon and your last carbon, which is often carbon 6, but not always, if they're pointing in the same direction, which in this case is up, it's beta. If they're pointing in opposite directions, then it would be alpha. So does anyone have any questions about that? Cool. So moving on to question number 6. Do we have a hemiacetal or a hemiketal?
I'm just gonna take a guess here. I'm not
Okay,
100%.
go for it.
Would it be a hemiacetal because the original sugar was like not a keto sugar, if that makes sense?
Yeah, exactly. So yeah, one way you can just drop it down. You can think about this is, if you're going to draw the sugar in the linear form, would it be an aldehyde or a ketone? And so, like you said, when the sugar is linear, it's an aldehyde. So when you cyclize it, it becomes a hemiacetal. The other way, if you're looking at the sugar and you're not sure if it used to be a ketone or an aldehyde, you would want to look at the carbon that used to be the carbonyl carbon, which is carbon number 1, our anomeric carbon. So if your anomeric carbon is bound to, if it has an H coming off of it, it's a hemiacetal. If this was a hemiketal, you would have another bond to a carbon over here. So this would be like maybe CH2OH or some other thing, some other hydrocarbon with hydroxyl attachment to it. Because in your, let me go back to our ketones that we were looking at before, because your carbon number 2, this would be your anomeric carbon. So hanging off of it, you would have carbon number 1 going up or down, in addition to this oxygen, which would become that hydroxyl group. That's either alpha or beta, which I know is a little bit maybe confusing. Oops, but you get the idea. So, oh yeah, I already had the linear form here, so you could look at that. So in the linear form, it used to be an aldehyde. And so there's this H hanging off of here that is ultimately also hanging off of our hemiacetal. That makes sense to everyone, hopefully, a little bit. Any questions about hemiacetals or hemiketals? All right, so now we can finally address question 7. So do we have a furanose or a pyranose?
pyranose?
Yeah, how do you know that?
Because it's 6 carbons in the ring.
Exactly. Yeah. Or did you say 6 carbons?
Yeah.
Okay.
right?
Yes.
Oh, sorry, not 6 carbons. There's 5 carbons in the ring, but there's 6 like members of the ring.
Exactly. Yeah. So we have a 6-membered ring, which is what defines a pyranose. This sugar also happens to have 6 carbons, but that's not what makes it a pyranose. It's because of how many items are in the ring itself. It's not a furanose, but a furanose would be a 5-membered ring. Any more questions about ring or cyclic structures of monosaccharides before we move on? Okay, so let's talk about disaccharides. So here we're looking at a disaccharide called maltose. And so the question is, what type of O-glycosidic bond is joining these 2 glucose monomers in maltose? And for each sugar, you want to consider the numbering of the carbons. Where is the anomeric carbon? Is it D or L? And is it alpha or beta? So take a few minutes here and look at these. Normally, I would encourage you to work with a neighbor, but might be tricky today. But go ahead and work on that, and we'll come back together in about 5 minutes. All right, so let's start thinking about these questions now. So first of all, what type of glycosidic bond do we see for these two glucose monomers?
Alpha 1,4.
Yeah, that's great. So how did you know that?
The oxygen on the anomeric carbon on the left is pointing down on a D sugar, and then it's bonded to the fourth carbon on the right sugar.
Yeah, exactly right. So we can start by looking at our glucose monomer that's on the left, and we can start to number our carbons. And so like you correctly identified, our anomeric carbon is carbon number 1. We have this OH group on the anomeric carbon is pointing down. And so, it's alpha. So that's the first part of the name of our glycosidic bond is alpha 1. And then the question is, where is it bound to on the second sugar? And so if we start counting the carbons in our second glucose molecule, we see that we're bonded to carbon number 4. So we can call this bond an alpha 1,4 bond. Does anyone have any questions about how we got there? Cool, great. So so let's think about these questions. So we just talked about how the carbons are numbered. We identified our anomeric carbon as carbon number 1. And we know that we are in, like someone said, the D configuration because our carbon number 6 is pointing up. And we know we're in the alpha configuration for our glucoses because our anomeric hydroxyl groups are pointing down. So they are pointing away from each other. That makes us alpha. And because we have a D sugar, that also means it's pointing down. Okay, so do we have, and then one other thing I guess is a good thing to mention here is how can we identify that these monomers are glucose? So we can look at that by looking at our chiral carbons. So when we have glucose, we're always going to have carbon number 2, hydroxyl pointing down, carbon number 3, hydroxyl pointing up, carbon number 4, hydroxyl pointing down. Whether number 6 is pointing up or down depends on whether it's D or L, but as we know, for D, it's pointing up. And then whether it's alpha or beta depends on what happened when the ring formed. But most of the time, when we're thinking about, just not most of the time, it depends what we're talking about, because glucose participates in a lot of different polysaccharides and disaccharides that we'll see. Excuse me. So, yeah, and so I guess the other way, if you wanted to think about this as or if you ever saw this as a Fisher projection and how to sort of arrive at where we arrived in this ring and how we know what's up and down and everything. So at the top of our Fisher projection, we have our aldehyde, we have our carbon number, and remember, so we have carbon number 1, 2, 3, 4, 5, and 6. So if we want to go back and forth from our sort of ring to our linear form, we can always imagine kind of taking our ring and rotating it back towards the left. So at our 2 carbon, our hydroxyl group is pointing right. At our 3 carbon, it's pointing left. At our 4 carbon, it's pointing right. And then we know it's a D sugar, so our 5 carbon is also pointing right. And so this would be what you have for glucose. And you can also imagine sort of tilting this linear structure 90 degrees to the right to sort of arrive at where we got for the ring with everything pointing up and down. Does anyone So yeah, so you should know for glucose at least, like what are the configurations at the chiral centers? Any questions about that? Okay. So that's monosaccharides and disaccharides. And once again, when you have these two glucoses linked together with that alpha 1,4 glycosidic bond, that disaccharide is called maltose. So that brings us to polysaccharides. And I think I've just skipped through these slides. Just 1 second. Okay, so now we can do our polysaccharides practice questions. So let's first, we'll just take a few minutes to think about the different functions of polysaccharides. So everybody take maybe 3 to 5 minutes and match all the functions to all the different polysaccharides. All right, so let's get started matching these up. So can anybody tell me what starch does?
It's the energy storage in plants and the dietary energy source for humans.
Yeah, excellent. So we eat a lot of starch in our diet, and it usually always originally from plants. So, all right, so let's now consider cellulose, which is number 2. So what does cellulose do?
D, structural stability in plants, not digestible by humans.
Yeah, exactly. So starch and cellulose, we see them both in plants, but they have different functions, and we'll see that reflected in differences between their two structures. So one of them is digestible and it's used for energy. The other one we cannot digest and it is more for providing structure. So yeah, so now let's move on to number 3, which is glycosaminoglycans. So what do those do?
They're a component of the extracellular matrices and connective tissues.
Yeah, exactly right. And then just so no one ever has to say glycosaminoglycans, we can always call them GAGs, because that is a very long word. And yeah, exactly right. So they're part of the extracellular matrix and connective tissue, and their structure also is what gives them this particular function. As we talked about, and as we will talk about later in the questions, they're able to hold on to water in a very particular way because of the different components of their structure and bonding. Okay, so now let's consider glycogen. What is glycogen doing?
B.
Yeah, exactly. So glycogen is what we use for energy storage. And so that finally brings us to chitin. What is chitin? The last one.
A.
Hey, excellent. Yeah, it's the one we didn't pick yet. So yeah, we see chitin in exoskeletons of invertebrates, and it helps to provide some structure. So in that way, it's kind of like cellulose, right? They're both very structural. Compared to something like starch and glycogen, these more have functions in terms of energy storage. And then glycosaminoglycans are also a little bit different. They're also structural, but in a very different way. They have very peculiar or particular properties to them that we will now get into. So this was function. Now we have a similar but different question about structure. And as we go through these, we're gonna keep those functions in mind because you'll see how their structure can sort of help each of these different polysaccharides have a particular function. So everybody take a few minutes again and decide if each of these polysaccharides is linear or branched. And we'll come back together in a few minutes and discuss. All right, so hopefully everybody has thought about these, all five. So let's get started with the first one, starch. So is starch linear, branched, or both?
Both.
Yes, starch is both. So for bonus, I guess, what are the types of starch and which one is linear and which one is branched?
The alpha amylose is linear and the amylopectin is branched.
Excellent. Yeah, so we have alpha amylose, which is linear, and amylopectin, which is branched. So starch as a whole can be either, but amylose is linear and amylopectin is branched. So let's skip around a little bit. Which other one in these of the four that are left, which other one is branched?
Glycogen.
Glycogen. Yeah, exactly. And so, and we talked a little bit about this in the lecture. So why is it important for there to be so much branching in glycogen? What does this mean in terms of the energy availability of all the sugar in there?
It's easier access to glucose.
Yeah, exactly. So the more frequent the branch points are, the more ends you have in a glycogen molecule. And then for every end, you can start cutting off glucose from the end. So if you have just one long chain, like in alpha amylose, there's only two ends, right? The beginning and the end. But if you have something like glycogen that has a whole bunch of branches, it's not the most beautiful drawing, but you get the idea. Now there's a whole bunch of ends. And so you can cut off a glucose from all those ends kind of all at the same time. Okay, and then what about the other ones if they're not branched, right? So what are they?
Linear.
Yes, all the rest of them are linear. Cellulose is linear, glycosaminoglycans are linear, chitin is linear. So so yeah, so we talked about each of these has a fairly different function, but a lot of them seem to have relatively similar structures, either linear or branched. So we have to sort of delve deeper now into the structures to figure out how those structural differences might cause a difference in function. And so this generally has to do with both what particular sugar you have in each of these polysaccharides, as well as the bonding between the sugars. So let's start talking more about those individual monomer subunits. So take a few minutes here, and for each of these polysaccharides, think about which types of subunits are in each one. So we'll come back together in maybe 4 or 5 minutes. All right, so hopefully that should be enough time to figure out which subunits are in which polysaccharide. So let's get started at the top again with starch. So what are the monomers that are in starch?
It's glucose, right?
Yeah, it's glucose. Which other ones have glucose?
Two, 4, and 5.
Yeah, so definitely cellulose and glycogen. So starch, cellulose, and glycogen are all entirely glucose always. Chitin is not just plain glucose. It often, or it does always have modifications to it, but it can start out as glucose. So, but there's a better answer for number 5. So, can somebody tell me what a better answer would be for number 5 for chitin?
The hexosamine.
Yeah, exactly. So a better way to describe chitin would be hexosamine. So the beginning part of hexose, meaning we have a 6 carbon sugar and it's modified by an amine. So in the case of chitin, we usually have an N-acetyl modification on that hexosamine. So, and whoever said glucose before was partially right. It is sometimes glucosamine and acetylglucosamine, but it's also sometimes an acetyl. Yeah, it's usually an acetylglucosamine. Sorry. So N acetyl glucosamine. So just as a reminder, that is usually on carbon number 2, but we don't usually write it that way because we can assume it's there. And we can also abbreviate an acetylglucosamine with this abbreviation, which you'll see maybe fairly often. So glucose, we can abbreviate GLC, and then N-acetyl. So it would look like this, GLC and AC, so N-acetylglucosamine. Okay, so that brings us to the glycosaminoglycans. So what do we usually see in terms of monomers for glycosaminoglycans?
C.
Yeah, so if you recall, so glycosaminoglycans are repeating disaccharides. So one component of the disaccharide is C, the uronic acid. And what would the other component be?
Is it E also?
It is so E. Yeah, excellent. So we have a uronic acid attached to a hexosamine, and then that disaccharide repeats to make our glycosaminoglycan. And so just as a reminder, does anybody want to tell me what does it mean to be a uronic acid? I guess everybody's getting tired. That's fine. So for a uronic acid, this is when we have oxidation of the last carbon's hydroxyl group to a carboxylic acid. So the last carbon is often carbon 6 for a 6-membered sugar, but not always, right? Depending how many carbons are in your sugar, the last carbon might be a different number. And so uronic acids are different from another modification, right? Onic acids. Does anybody remember what the modification is when we see an onic acid? Okay, so an onic acid is when we have oxidation of the aldehyde to the carboxylic acid. So, all right. That is enough for the subunits. So let's just go over one more polysaccharide question, and this time we're going to talk about the bonds. So I guess to lead into this, we talked about on this slide with the subunits, we have 3 very different structures that are all entirely made of glucose, right? Starch, cellulose, and glycogen. So what is the difference? And they all have very different functions that we talked about when we first started discussing polysaccharides. So the difference that we see between them has to be with the bonding that we see. And then there's also, of course, differences in bonding with GAGs and chitin as well. So we'll get into all of those. But that's why it's so important to remember or consider what types of glycosidic bonds you're looking at, because the different bonding can lead to a particular structure, which again leads to a particular function for a polysaccharide. So everybody take a few minutes here. Think about what types of glycosidic bonds we're looking at for each polysaccharide, and we'll come back together in 3 or 4 minutes.
Professor Kotzev, can you please go back one slide?
Sure.
Thank you.
Okay. Did you just want to write something down, or you had a question?
No, I just needed to write something down.
Gotcha. Okay, cool. So I'll just flip back to this one so people can reference it. Okay, so let's start thinking about the glycosidic bonds that we're seeing. So let's start with number 1 with starch. What glycosidic bonds are we looking at?
A and C.
Yeah, exactly. So we have some alpha 1, 4 and some alpha 1, 6. So why does starch have 2 different types of bonds? Are they doing different things in the starch?
One is for the branched form and one is for the linear form.
Yeah, exactly. So all of the linear parts are alpha 1, 4. Every time you have a branching off point, you have an alpha 1, 6. And then once you make that first branching off, then all the other glucoses that are part of that branch will be connected to each other in a line in the 1, 4 bonding. All right. What other polysaccharide in this list has those same 2 types of glycosidic bonds, the alpha 1, 4 and alpha 1, 6?
Glycogen.
Yeah, exactly. So glycogen also has alpha 1, 4 and alpha 1, 6, and they're doing the same exact thing. The alpha 1, 4 is for when you have a line of glucoses, and alpha 1, 6 is when you're making a branch point. And so I just also want to be really clear for starch. So alpha amylose is only alpha 1, 4 because alpha amylose is only linear, and amylopectin has both of these types of glycosidic bonds because amylopectin is branched. For glycogen, glycogen is always branched. So for glycogen and for amylopectin, what is the difference between them? They're both made of glucose monomers. They both have the same exact type of glycosidic bonds. So how do we tell the difference between amylopectin and glycogen?
Glycogen, aren't they like clusters of 10? Or like, oh, besides the branching? Is that the question?
So yeah, so you have the right idea. So glycogen, the branching occurs more often. So more frequent branch points. So I think for amylopectin, it's something like every 25 glucoses, you have a branch point, compared to glycogen, where it's about every 10 glucoses, you'd have a branch point. So they're more frequent. So you have more branches overall, which again relates to the ability of having more ends available. So the more branching you have, the more individual ends you have on any big glycogen polysaccharide. So you can cut off more single glucose molecules from each end of each branch at the same time when you need that energy. Okay, so let's now think about cellulose. What types of glycosidic bonds do we see for cellulose?
I had a quick question about glycogen.
Sure.
So I know that it's only branched. So when you say like the linear is alpha 1 to 4, is that just the linear part of the branch?
Yeah, exactly. So if you imagine glycogen as, you start out with a line. These are all connected with alpha 1, 4. Every time you make a branch point, that branch point is connected by an alpha 1, 6 bond. But then all the other sugars in each line is connected by alpha 1, 4. Does that
Yeah, that makes
kind of help?
sense. Yeah,
Yeah.
thank you.
Okay. Excuse me. Okay, so yeah, so let's think about cellulose. What kind of glycosidic bonds do we see in cellulose?
Beta 1, 4.
excuse me, Alexa, stop. Sorry about that. What type of glycosidic bonds do we see in cellulose?
Beta 1,4.
Yes, we see beta 1,4 bonds. And so we talked about before, cellulose is also made of all glucose, just like starch and glycogen, but the big difference now is this bonding, this beta 1,4 linkage. And we, as humans or as mammals, we lack the enzymes that help us break down those beta bonds. And that's part of why we cannot digest cellulose, but we can digest starches and we can break down glycogen. All right, so what do we see in chitin? Let's skip over to number 5. What kind of bonds do we see in chitin?
Also be?
Yeah, exactly. So chitin also has those beta 1,4 bonds, just like cellulose. So cellulose and chitin have the same bonds. Starch and glycogen have the same bonds. So the big difference between chitin and cellulose is not the bonding, it's the type of monomer, right? Because cellulose has those glucose monomers, but chitin has those hexosamine monomers. So same bonding. So we can't digest either of them. If we were gonna eat some invertebrates with exoskeletons, we could not digest their chitin either, just like we can't digest the cellulose from plants. Any questions about beta 1,4 bonding? Cool. Okay, so now let's consider our GAGs, our glycosaminoglycans. What type of bonding do we see there?
Beta 1,4 and beta 1,3.
So yeah, you're kind of on the right idea. So it depends. It varies. It depends on what individual like disaccharides or components you have of the individual subunits that are making up your glycosaminoglycan. So we looked at a few examples in the lecture slides, but that's just a few examples. There's like a big variety of glycosaminoglycans. So depending on what the individual monomers and disaccharides are, you can have some amount of variation. So yeah, we can just say it varies. It depends. So yeah, so I have a sort of maybe one last kind of bonus question about this. So we didn't choose choice E, right? And this choice looks different from the other ones. So for all the other ones, the one of the carbons is named as the anomeric carbon, it's alpha or beta. And then the second, so like if we look at part A, we have our anomeric carbon is the number 1 and it's alpha and it's bonded to a carbon number 4 on our second sugar that's not anomeric. So in choice E over here, we have 2 anomeric carbons that have a glycosidic bond with each other. And you can tell that because of the way it's named. So your first carbon participating in the bond is anomeric and it's in the alpha position. It's on carbon number 1. That would be bonded to another anomeric carbon. That anomeric carbon, the hydroxyl group is in the beta configuration and it's on carbon number 2 of that sugar. Does anybody happen to know where we would see what type of sugar has this particular glycosidic bond? It's okay if you don't. It wasn't necessarily, I don't think, part of the slides, but we see this in sucrose. So sucrose is a glucose attached to a fructose. And so you have, and they're attached at their anomeric carbons. So you have the alpha glucose attached to a beta fructose. Fructose is a ketose, so your anomeric carbon is carbon 2. Whereas for glucose, your anomeric carbon is carbon 1 because it's an aldose. And then the other thing to note about these types of glycosidic bonds where the anomeric carbon is bound to another anomeric carbon is you generally can't find them in polysaccharides. So for polysaccharides, you kind of want each sugar to be able to look kind of the same. So all the anomeric carbons are, facing on the right side, and that way they can bond to the left side of the next sugar. In the case of something like sucrose, we have 2 anomeric carbons bonded with each other and facing each other. So now if you wanted to add another sugar onto there, you kind of used up all the anomeric carbons making this one bond in between the glucose and the fructose. So there's nothing else to kind of add onto. And so that's why you generally won't see this type of bond in a polysaccharide. So any questions about that or anything else about polysaccharides? Okay, so I think we've reached a sort of good stopping point for today. So we'll pick up on Thursday with our glycoproteins, and hopefully by then we'll be in person. And just for anyone, if you were planning to come to office hours, I'm obviously not in my office today, but if you want to chat with me, I'll be on this Zoom link until 3 o'clock, just like for normal office hours. So you can either just stay on the call or join back in anytime before 3, and I will be here if anyone wants to chat. So that being said, I'll stop the recording, and everybody have a great rest of your day.